So this is my math project, Hilbert's Paradox of the Grand Hotel. And some background on this paradox is it was first proposed by German mathematician David Hilbert in 1924 during one of his lectures, but it only really became widespread in the 70s when more people knew about it. But Hilbert claimed basically that a hotel with infinitely many rooms at full occupancy can still accommodate more guests. Now you may be asking, how could a filled infinite hotel possibly accommodate more people? Because it's a filled hotel, how could there be more rooms if every room has a person inside of it? And this is where the paradox part comes in. Well, Hilbert's statement isn't only true, but it's mathematically provable. So first we'll just start with a little example. Imagine one guest comes inside looking for a room. So they only need one room. So what we can do is guest one can move to guest two's room, guest two can move to guest three's room, and this can happen infinitely. So somebody is moving into a room, and the person in that room moves to the next room. And that happens forever with everyone, but that basically leaves room one open for one guest, that one guest that's waiting for a room to come inside and start staying at. So we can prove this for not just one person, but every person. So let's say the room a current guest will have to move to is R equals C plus N. So C will be the guest's current room, N will be the number of new guests inside the lobby, and R will be the room that they will have to move into, the current guest. So for example, if 20 people come into the hotel looking for a room, guest in room 7 will have to move to room 27, guest in room 27 will have to move to room 47, and this will happen for everybody until 1 through 20 is left open, and those 20 people can come in, and everyone's going to keep being moved all the way until infinity because everybody's going into a new room to fit everybody in. So for infinite guests, Hilbert not only proposed that the hotel could accommodate finite numbers like 1, 2, 3, 4, but infinitely many guests could come in looking for room and still be accommodated. But before we get to why, what do you think is the reason why this could happen? Because, like, how do you think we could mathematically prove this? So if we think about the first scenario where people were repeatedly moving over and over to new rooms, we could theoretically see how infinite people could fit in if people would just keep moving over and over again. But we can actually prove this mathematically by keeping the R and C from before and making a new equation called R equals 2C, which is where the current guest will move into based on where the room is. So they just go into the room, double their current room number. And this equation works because whenever any number is multiplied by 2, it becomes even, and that leaves every single odd number open. And since there's an infinite number of odd numbers, infinite number of even numbers, all of those infinite people who are currently inside of the hotel and they're in infinite even rooms, every infinite person that's coming in to get a room can move into those odd rooms. Now, before we start our final scenario with the hotel, we'll have to step away from the hotel a bit to talk about prime numbers, which we need Euclid's proof to prove that there are an infinite number of prime numbers inside of our set of infinite natural numbers, which is the amount of rooms in a hotel. So we know that a prime number is itself times 1, so its only factor is itself. So if we multiplied every hypothetical finite prime number together, we would get this number x. But if we added 1 to x, we would end up with another prime number because we're not able to take any of the factors that we use to multiply to make that x out of x plus 1. It's just not possible because we've taken out every possible number that we can do to make it work like that. So we end up with another prime number that isn't found in the finite prime numbers that we have. And even if that's not enough, we can keep doing this and keep getting x plus 1 with these new prime numbers we're finding, and we'll never reach a limit. So if there cannot be a finite amount of prime numbers, therefore there has to be an infinite amount of prime numbers because there's no other option. With that context, we can now move into our final scenario, which includes infinite buses of people. So at first, we're going to start with finite amount of people. So this equation actually gets a little bit more trickier. We have R of nu equals P to the Q. And Q will be the passenger number, so passenger 1, passenger 2, passenger 3. And there can be passenger ones on every single bus, but there can't be two passenger ones on one bus. um, P will be whatever the bus number is plus 1 and that element of a set of all prime numbers, which means that if you were on bus 1, you would have the second element of a set of all prime numbers, which would be 3, If you had a bus number of 2, you'd be the third, which would be 5. But we have that plus 1 because we can't have 2 as a prime number, because then as we get on to later, that just doesn't work with what we're trying to do. And finally, RNU will be the room of a selected guest on the bus. So now we'll get into a little bit of reasoning behind this equation. So every prime number except 2 is odd. That's why we added 1 to the bus number at the beginning in P. And every odd number multiplied by odd has a product of odd. So every prime number times a prime number equals a prime number. And every prime number to a power would be a prime number to a prime number, which means prime numbers times prime numbers equals odd. Prime numbers to a power don't overlap with other prime numbers to a power or themselves. So like unlike 3 and 9, which 3 to the second power is the same as 9 to the first power, but you wouldn't have that with any other prime numbers. 3 to any power will never equal 5 to any power, and that works for every single prime number. And since we have infinite numbers of prime numbers because of Euclid's proof, then that means we have infinite numbers of prime numbers that we can infinitely go to find these rooms, because we're able to go into every odd room. And if we have all odd rooms, they're open from the R equals 2C equation, and we have infinite prime numbers, we can infinitely repeat this thing for infinite buses. Now we can use all this reasoning to prove that infinite buses of infinite people actually still is accommodated in the hotel. So let's start with P. P was dealt with the bus number, and if we have infinite prime numbers because of the Euclid's rule, we already have infinite buses ruled out as being able to be accommodated. But what about infinite people? There are infinite people, which means there will be infinite amounts of natural numbers for the people to take, but we know that any prime number to a power is its own distinct number compared to any other prime number of a power. So you can infinitely go from that 3 to whatever number will never match up with any other prime to a power, even if it's the same exact power that it's up to. This hotel can fill in the role for an infinite set of all natural numbers, and the guest can fill the role of new elements as long as they're in the set of natural numbers. Because you can repeatedly put these guests inside of the set, these elements inside of the set, and it will never be full. You can put as many guests as you want, even infinite guests. And we can take this one step further with the buses, as setting them as their own natural number sets, either finite or infinite, and we can still add the elements of those sets inside of the original infinite set of all natural numbers. Thank you for watching.